Hey Fizz1 kids, Campbell here. In this video, we're going to talk about sound waves and the Doppler effect. Now, if you remember when we talked in the first video about types of waves, we said that a sound wave was a good example of a longitudinal wave. Remember, longitudinal waves are where the wave medium is traveling in the same direction as the wave. Well, sound waves are also called pressure waves. And if you've ever been to a concert with very loud music, you know why, right? You can feel the beat hitting your body. But it's because what sound is, it's a compression and moving away of the air molecules. And so when those air molecules hit you, it's kind of like wind, except boom, more of a vibration. Now, in a sound wave, the regions of the higher pressure are called the compressions, and the lower pressure is called a rarefaction. But we can still graph a sound wave just like we do a transverse wave. But here we're graphing the pressure versus the pressure of the atmosphere, which is the normal pressure. Now, just like all waves, the speed of sound is dependent on the medium it's in. And for speed, the denser the medium is, the faster the wave moves. And it's because those molecules are closer together. So if the molecules are closer together, the sound wave can travel faster. So it travels faster in a solid versus a liquid versus a gas. And you can see here in diamond where you have real tight packing, right? That's a covalent network solid. You have very large speeds. Whereas if you go into air, the typical air speed is about in the 340 range. So sound moves faster when the molecules are packed in tighter because it's a vibration of those molecules. Also, because temperature, right, affects the motion of molecules, sound velocity increases with increasing temperature. So here is an equation. This is the speed of sound at 0 degrees Celsius, 331 meters per second. And so for every degree above 0 degrees, if we multiply that temperature by 0.6 and we add it to 331, we get the speed of sound at that temperature. So this is an example. If we multiplied 0.6 times 20 and we added it to 331, we would get 343. Now what that means is when you're solving problems with sound, you need to know what the temperature is so that you can use the correct speed. So that would have to be given to you. Here is an example. We hear sounds from a wide range, actually, from a frequency value of 20 to 20,000 hertz. And the mid-range of our hearing actually is about 500. Higher frequencies, you start to lose when you get older. And in class, we're going to take a look at how frequency, how well you can hear frequencies. So if I want to know what those wavelengths are, we would use what I call the velocity is for lambda equation. And like I said, when you're going to calculate something with the speed of sound, you need to know what either the speed is or what the temperature is so you can calculate it. So wavelength then is that speed of 343 divided by the frequency. So if we go through and do that for each of these, right, the bottom range of sound would be 20 would be 343 divided by 20, right? That's about 17 meters. That's a pretty long wavelength. Interesting enough, light wavelengths are in the nanometer range, so big difference between sound waves and light waves. For our mid-range, we would divide by 500, and of course, that's about 0.69 meters or 69 centimeters. And at the upper range, which I can tell you I don't have much of an upper range anymore at this age, is 0.017 or 1.7 centimeters. So velocities for lambda is our equation, and the speed needs to be given so we can solve, or the temperature so we can find the speed, because it changes with temperature. Now, there's certain sensory effects that have an actual physics name for them. So when we think of loudness, right, you think about how loud that sound is. What the loudness is a reflection of is the intensity or the amplitude of the sound wave, how much energy there is in the wave. Whereas pitch is that frequency. So when you're talking about the pitch, increasing the pitch, we're talking about frequency or increasing the frequency. Now, sound is a spherical wave, so it moves out in all three dimensions. And of course, the wavelengths are the distance between those compressions or those rarefactions as the sound wave propagates out. The intensity of sound, or the loudness of sound, depends upon the power. It's really a reflection of how much energy there is, and it's the power per unit area. Because it's a sphere, right, the area of a sphere would be 4 pi r squared, which makes the intensity inverse square rule, kind of like the force of gravity was an inverse square rule. So intensity decreases with the square of distance from the sound source. That's why we call it an inverse square rule, which means that every step you take away from that speaker, that intensity drops by a square. Get away from those speakers. It's not good for your ears. Now, the loudness of the sound is called the sound intensity level, and it's a logarithmic scale. And it's what's interesting is the perceived loudness is actually much less than the actual intensity of the sound. Our threshold of hearing, which is the lowest intensity that could be heard on the loudness scale, would be 1 × 10 to the negative 12 watts per meter squared. All right, that's our intensity, right? Power per unit area. Because of these numbers, and they change by a logarithmic scale, we use actually an intensity level unit called the decibel. So the decibel is actually a conversion factor that we use instead of talking about watts per meter squared. One of the really cool things about sound is the Doppler effect. What do you think is going on when you hear this sound? Sounds like a siren just went by you, right? And I bet you could envision it as the siren was approaching you and then it went past you. Well, that is the Doppler effect. What the Doppler effect is an apparent change in frequency of sound when there is relative motion of the source and the listener. So if something is moving, either the source that's making the noise or a person is approaching or leaving the source, they will hear a change in the frequency. Now, the reason for that, right, we have this circular sound wave, the spherical sound wave. And let's say that at t equals 0, here's where the sound wave is. Maybe this is the ambulance that we just heard. And it's approaching Nancy over here. Well, as it emits the sound wave, it's traveling in the wave. So the wave fronts here get smaller. And remember, wavelength and frequency are inversely related to each other. So if wavelength goes down, the frequency goes up. So the frequency is higher as it approaches us, but behind us, if it's moving away from us, right, those sound waves are getting farther apart. All right, so it's really easy to hear that drop in the frequency of the wave, or the sound wave, that you can hear that pitch going down as it goes by you. But it's because it's moving, and so as it moves, the wave fronts are bunching up on itself, and behind they're getting farther apart. Well, I've got this really great animation, thanks to Australia, where we can actually see this. So let's listen to it first. This is a little hard to hear. It's high-pitched frequency. All right, so you heard it approach you, and then you heard it go away. So the pitch went up as it approached you, and it decreased as it went behind you. Because what's happening is this. Here's my speaker emitting the sound, right? And it emits a spherical wave that travels outward, but it is catching up to the waves it emitted in the beginning, and it's moving away from the waves that were behind it. But it doesn't just have to be that the thing emitting the sound is moving. It could be that you're moving at the sound. So whether you're moving or the sound is moving, you still get this effect. Now, let's look at why that is. So here is a fixed source that's emitting spherical waves, and here you are on your bike, and you are approaching the waves. And so now let's watch what happens as you move away and we get another biker coming in. and how many wave fronts they hit. So the number above them is how many wave fronts they hit in the same period of time. You'll notice the person approaching the wave is, because they're traveling towards the wave, are hitting more waves. So more waves means that the apparent frequency will be higher because the wavelength, or at the time that they approach those peaks, is less. Whereas if you're moving away, right, you're going away from it. So the frequency, the perceived frequency, decreases because there's more space between the waves as you approach them. So Doppler effect's pretty cool. So for the Doppler effect to occur, this perceived change in the frequency, that pitch, it doesn't matter what's moving. Either the source of the sound could be moving, the person hearing the sound could be moving, or you both could be moving. What you need to know is that how much the frequency changes from the source, the actual frequency of the source, depends upon both the speed and the direction of the movement. So if that source of sound is moving towards the observer, or the observer is moving towards the source, they will hear a higher frequency because they're hitting the wave fronts quicker. If the source of the sound is moving away from the observer, or the observer is moving away from the source, or both, then the observer hears a lower frequency because as they hit those wave fronts at a longer period of time. So the Doppler effect is the perceived change in frequency due to the motion of the source or the observer or both. You won't have to calculate it, but you need to know how it changes in terms of higher or lower frequency depending upon speed and motion. So the last thing I want to talk about in this video is what a shock wave is. So if you've been around at some of the air shows when the Blue Angels have been flying and you hear that big boom, and when they're practicing over our houses during, like when they're getting ready for the air show or the school, right, you can hear the loud noise. Well, why does that happen? Well, it's because anytime anything is moving faster than the speed of sound, which is possible, right? Speed of sound is only 343 meters per second. It's not like the speed of light, so you can travel faster than that. What happens is all those sound waves are piling up on each other because you're moving faster, so you don't even actually hear it if you're in the plane. But people on the ground get this big overlapping wave of large amplitude, and it produces boom, shock wave, and we call that a sonic boom. So that's because it's moving faster than the speed of sound. So if you're in that plane, you don't hear it. But if you're on the ground, those waves are bunching up on each other and ow to the ear. All right, fill out your WSQ and I'll see you in class.